So, continuing from last week, we are still on the particular nature of matter. And if you remember last week, we started with the state of matter, specifically looking at solids, liquids, and gas, where we learned a number of things about them. I'm not going to say it, but for me to be sure that you remember, I'm going to do a short test on it. So quickly, on the state of matter, solid, liquid, and gas, let's do this review question which I'm doing right now. So first thing you are doing for me is that using a diagram, show how the particles of solids, liquids are arranged. Then the second question you're supposed to do is you mention at least two properties of the state of matter. So let me give you like a minute. Quickly, draw the diagram for me. Let's see. Okay, so for the first one, ideally if you do it right, your answer should look somewhat like what I have on the screen. If you do it right, your answer should look like this. So how many of you are able to do something? Show me. Show me what you did. Okay, that's very good. Vanessa, good. That's good. Alright. The second property, the second one is the property of the state of matter. Solid, liquid, and gas. What are some of the properties of solids, liquid, and gas? First.
Fixed shape.
Yeah, the fixed shape. Let's see if it's part of the answer that we got. So solids have a fixed shape. How many of you got fixed shape? Solids. Okay. Can you give me another property of liquids?
Yeah, atoms aren't as tightly packed as solids.
The atoms are not really tightly packed, which is good. Any other one can give me another property of gas? Gas, yes. The particles are really free. So the answers before we do what you said and somewhat like what we have here. Good. If you're going to do it, that's good job. Let's move on. For today's lesson, we are going to start off on the last part of what we did. Last week, we also looked at the changes in the state of matter. How many of you remember that we did a change in the state of matter? Great. Let's see. Quickly, within 30 seconds, we have to find the processes involved when liquid changes to gas, gas to liquid, and stuff. I'll show you the ideal answer when you are done with it. Quickly, let's see. So what would be the process for A, solid changing to liquid, and then liquid changing to gas? Just pick one and answer, and I'll ask you at the end of it. Alright, so let me ask, Lena, the process by which solid changes to liquid? Melting, very good. Then the process by which liquid changes to gas? Gideon? Evaporation. What about gas changing to liquid? You, gas changing to liquid? Condensation. And the last one is the process. Can you give me an example of liquid changing to gas? Any particular matter that changes from liquid to gas? Any? Yeah, you. Water to water. Very good. Alright, very good. So if you did it right, your answer should be somewhat like what we have here. And I believe most of you are able to do it. That's a good job you've done there. So for today's lesson, we have only two objectives. The first one is, at the end of the lesson, you should be able to explain the changes in the state of matter that we learned in terms of kinetic theory. And then two, we should be able to describe qualitatively the pressure, the effect of pressure and temperature on gas in terms of how they move. So these are the simple objectives we are going to do. So I need you to pay attention and be with me. So let's get started. The key terms we are going to be seeing as we move through this lesson are, some of them are, we have kinetic theory, we have particulates, we have absolute zero, we have collision, and then we have implosion. So at the end of the lesson, if you do a good job, these key terms will appear and you will get a concept of it. Moving on. So temperature. When we learned the changes in the state of matter, we saw that liquid can change to gas, then solid can change to liquid. What affects the state of matter that makes it to change? And then we saw that temperature was key So if you look at the temperature heat graph as we have here, if you take a solid line, as temperature rises, the solid begins to change from its state gradually. Then when it gets to this point, here, it begins to go through the change of solid or ice to liquid. This particular phase, we actually call the latent heat of fusion. What it means that the heat that is required to change solid to what? Liquid. At this particular point, the temperature remains constant. So if you've seen ice that is melting, you have the ice form and then a bit of water. How many of you have seen something of that sort before? Ice is in the process of melting. There's ice and then there's water. That is what we have here. At that particular point, temperature remains constant. Are you good? Yes. Then when it has fully melted to liquid, then the temperature begins to again what? Rise. And then it gets to a phase where you have to change from liquid to gas, the gas-liquid interface. Then we have this phase which we call the latent heat of what? Vaporization, the point where vaporization starts. At this point too, temperature remains constant. Then once the liquid has changed it's entirely to gas, temperature begins what? Rise again. I hope you do get it. Alright, thank you. So let's look at another graph in terms of real numbers. So we know that our temperature do water change to ice. Our temperature, anybody? Nathan? So 0 degrees and below, water will change to ice. So if you look at what we have on the screen, the graph, from minus 20 to 0, we have the ice phase. Then when it reaches the ice phase, at this point, temperature is the same because the ice is no more ice, it's between ice and then water. You get the concept? Then begins to rise. That's what we call the ice-water interface. From there, for it to become fully water, temperature begins to rise all the way to 100. And what do we know happens at 100 degrees? 100 degrees with water,
water begins to boil. At
100 degrees, water begins to what? Boil. That means the water is changing from normal liquid to become water vapor. To become water vapor. So you see the water-steam interface, the temperature is also what? Constant. Are we good? Then once it gets to the steam end of it, temperature begins to rise again. So temperature is very key, whether high or low, in the changes in the various phases of what? Matter. For solid to liquid to gas and then likewise backwards. Alright. Kinetic theory. We learned in energy, and I believe we've learned that before. Kinetic energy. Anything you know about kinetic energy? Anything you know about kinetic energy? Yes, fine.
The energy possessed by objects in motion.
Energy possessed by objects in what? In motion. So once an object is in motion, it has what? Kinetic energy. How does temperature affect motion or kinetic energy, which we call what? Kinetic theory. We learned this when you're looking at heat energy, that once atoms absorb heat energy, they become, anybody can help me? You? They become excited, and at that point they begin to what? Vibrate. They begin to what? Vibrate. So what happens is, look at this diagram we have on the screen. At a high temperature, the atoms are excited. The atoms are excited. You get it? Because they are excited, they are moving. Two of us. Look at what you have here. And as they are moving, initially they were here. The volume was small. Then high temperature, they are excited, they are moving, they are vibrating. So what has happened to the volume? From what you see on the screen, this is the initial volume, this is the final volume after it's heated. What has happened to the volume? What has happened to the volume? Yes, the volume has what? Increased. Why? Because they've absorbed energy and then they are moving. So they are moving everywhere. Do you get the concept here? So now, what is the effect of temperature on gas molecules? This, the first one I've done for you. Let's see. The first thing is, when gas have a low temperature, their kinetic energy is what? Their kinetic energy is also what? Also low. Because they have a low temperature, that means that what? They are not excited enough, that means their movement is restricted. Be clear? Yes. Awesome. But when they have a high temperature, what happens to their kinetic energy? It increases. That means that their movement also increases. Are we clear?
Yes.
So now, let's ask, in terms of speed, at low temperature and then at high temperature, which one will have more speed? This is for you. In terms of speed, at low temperature and high temperature, which one have more speed? Nathan?
The one at high temperature.
The one at high temperature. So let's see. So when temperature is low, gas molecules have what? Low speed, because they are not moving enough. And then when temperature is high, they have what? High speed. And like we said for the volume, because temperature is low, they are not occupying enough space because there's limited movement. So they have small volume, but when temperature is high, they move a lot and they have what? Large volume. Are we clear? Yes. Any questions so far to this point? Okay. Alright, so we'll be doing something for you very soon. So the key thing I need you to look here is that temperature affects the kinetic energy of atoms, which in turn affects what? The speed of the gas molecules. And also pressure, which we look at the next slide. Pressure is also another factor which affects kinetic theory. As to how it does it, we are going to look at it in the next slide. So this is basically what we explained here in the previous slide. Standard, this is the size, this is the volume. When temperature is high, see that the volume has increased, true of course. But when the temperature is low, what has happened here? The volume has decreased because there's less movement. So the bottom line is, temperature is high and low. So at the lowest point, there's a point in temperature that there's no vibration. We know that when there's low temperature, the particles don't have enough kinetic energy, so their movement is restricted. We've established that in the previous slide. But does it mean that they continue to vibrate? At this point, minus 273 degrees Celsius, which we call absolute zero, any atom stops moving. There's no movement. And when you reach this temperature, there's no movement. So if you have here, we have the helium balloon. When they pour liquid nitrogen into it, all the particles in it stop moving. So the point at which temperature or vibration of particles stop is what we call absolute zero. And the value is minus 273 degrees Celsius. Before we go to pressure, I want you to do something for me. First, draw two boxes to show the effect of temperature on the volume of gas molecules, whether it will increase or it will decrease. So we have our technique. It will decrease. All right, great. So, Ryan, let me see what you've done. Okay, show what's over to the camera. Let me see what you've done. Okay, there was a beautiful what's going on here. That's nice. Okay, very good. It's done very well. So, let's look at the effect of pressure on gas. Effect of pressure on gas. Pressure on gas comes as a result of two things happening. The first one is this. This is the box. Imagine this. Pressure comes when there's what? Collision. You get it? So one hits another, or there's a hit in between two things. There's something in contact. So if they are close and they are small box, like let's say if we are one box and we are here, and then we are small, would we be touching each other more frequently or less frequently? Why? Because we have a smaller volume. You get the idea. So the same way, pressure happens in two ways. One, among themselves, they hit each other. As they are trying to move, and I'm trying to move, I hit you. He hits me. In that order. At the same time, too, it happens when the particles hit the walls of the container. But what actually goes on? Let's look at how this is what happens with gas molecules with pressure in a container. So this is how they are moving. So there's a high chance that you will hit another atom or you hit a container. Are we clear? Alright. So how do we see this? How do we demonstrate this? we get to experience pressure in diverse ways. Another form of pressure is called atmospheric pressure. And this thing, atmospheric pressure means the pressure around something. So let's say I pick a can here. Okay, there's pressure. You know that this has a drink in it, so you store the pressure inside. Atmospheric pressure, the pressure was around it. Do you get the concept? Now, if I tell you that that tank you saw, nobody did anything, it just became like this because of pressure. Nobody touched it. It became like this. How many of you believe? Or how many of you have a doubt? Oh, show me. How many of you believe? Have a doubt. So this is a tank which was in a real tanker, and what they did was they cleaned the inside using steam, and steam is gas molecules. So because it's steam, gas occupies a large volume. You get the concept? But when the gas molecules condense, that means their volume became what? When their volume became what? It means that the pressure it was having initially has now reduced. Meaning the pressure around it, the atmospheric pressure is now more. You get the concept? And because of that, it causes it to crash. So let's watch a quick video on how this thing happened. A quick video on how this thing happened. How many people know what happened? So it was just there. So the tank was just there. But because the pressure inside was smaller than the pressure outside, it caused it to what? Implode. So when pressure, atmospheric pressure causes you to what? Submit in. That's what you call it, implosion. And we are trying to see if you can demonstrate this one before we end the lesson. So as we have our system heating, let's see if we can demonstrate. Very short time. Demonstration to depict what it's talking about. So it's called the crashing can. It's a simple experiment. So all we do is that we need a can. You can see here we have water in this can. And then we have water. So the first thing we do is we fill the can with water. With enough water. Then we set the can on the heat source. Set the can on the heat source. So our heat source is the hot plate. Then we allow it to boil to the point of steam. You get the concept? You have to be careful because you are dealing with what? The heat source. If you're not careful, that is hot water can actually end up burning yourself. You don't want any of that. So you have to be careful. That's why today I am doing this experiment for you to see. Later we'll do the experiment together, individually, using the main science lab. Alright, so I think our water source is quite ready now. So let's take it off the heat source. Yeah, these are improvised. Alright, so we're going to lift this thing gradually off the heat source. And the first thing is immerse it here. So what happened? What has happened to this? What has happened to it? It imploded. Why do you think it imploded? Dude?
The gas pressure in the can was less than the atmospheric pressure.
The gas pressure in the can was less than atmospheric pressure. And because of that, like what was in the video, if the pressure outside is more than the pressure inside, it causes the whole situation to work, the whole container or what? Implode or crashing. Do you get it?
Yes.
Alright. Did you enjoy the lesson?
Yes.
Alright, so on that note, I'll see you again in the next class. Have a nice day. Bye.